morning. Good morning and welcome to the Equinox Summit from the Waterloo Global Science Initiative. WGSI is a partnership between the University of Waterloo and Perimeter Institute here in Waterloo, Ontario, Canada. Welcome to our many guests in the theatre, and welcome to those of you tuning in online and on demand. This session will run approximately 90 minutes long, including the question and answer period. The Q&A period will include a healthy dose of conversation with our Forum of Future Leaders. These are 20 to 30-year-olds who are here from all around the world in a number of different backgrounds. And they're working quite hard with our energy experts this week. The forum will be contributing to the Equinox communique that you'll hear more about tomorrow that will help map out a cleaner and more electrified future. A reminder now to please turn off your cell phones and any other personal devices, and we'll start with our moderator in just a few seconds. Thank you.
Thank you, John. Welcome back, everybody. Ladies and gentlemen, welcome to Day 3 of the Equinox Summit Energy 2030. My name is Wilson De Silva, and I'm the Editor-in-Chief and co-founder of Cosmos, science magazine in Australia. I'll be serving as your host and moderator today for our Summit plenary session. What you will see this morning is an insight into the discussions we are having in the working sessions. I've been helping to moderate them, and I can report to you that we are making valuable progress. We are engaging in open, candid, cross-disciplinary and intergenerational dialogue that is bearing real fruit. So stay tuned. Okay, in the first 4 rows of this theatre, there are 40 people, scientists, engineers, entrepreneurs, and future leaders, who are working to create a joint vision on the transformative technological solutions we will need over the next 20 years and beyond if we are to begin realising a cleaner, more sustainable energy future. And I've got to tell you, they're doing an excellent job. Every morning we begin with a public plenary session like this one, in which 4 summit participants propose innovative technologies or approaches with the potential to transform our energy system. Each of them will deliver a 10-minute presentation arguing their case. Today's session is Ensuring Electricity: What Happens if the Lights Go Out? We'll examine some of the emerging technologies and approaches for meeting global demand as we rely more and more upon electrical systems. Following the presentations, we'll explore their ideas in a panel discussion and audience Q&A. But let me introduce you to our panelists. Bill Rosehart is a professor at the School of Engineering at the University of Calgary who studies the optimization of power systems. Maria Skyllas-Kazacos is a professor emeritus at the School of Chemical Sciences and Engineering at the University of New South Wales and has done pioneering work with large-scale batteries. Ted Sargent is the Canada Research Chair in Nanotechnology and a professor in the Department of Electrical and Computer Engineering at the University of Toronto. He has made contributions to the development of solar cells and light sensors based on semiconductors. Walt Patterson is an Associate Fellow in Energy, Environment and Development at the UK's Royal Institute of International Affairs, known as Chatham House, and a Visiting Fellow of the Science Policy Research Unit at the University of Sussex. But before we start, let's take a look at a short video that will set the tone for our discussions. This video explains the state of battery storage today and why it's going to be an important part of our energy future. Let's take a look.
We produce some 22 trillion kilowatt hours of electrical energy every year, much of which gets lost or dissipated through generation, transmission, and inefficiencies. If we could somehow recapture or store this wasted energy in batteries, it could dramatically slow down our rate of CO2 emission. But surprisingly, today's battery technology isn't that far removed from the acid batteries used in the American Civil War. Despite some advancements, our current batteries can't store and deliver power with the sustained punch, performance, and portability of other sources, like oil, natural gas, and coal. But if they did, we could store electricity from variable sources like the sun and wind and other low-carbon sources, and then use that energy on demand. Battery limitations can be best illustrated by the current state of electric-powered vehicles, which can travel about 160 kilometers before they need a recharge. But to be comparable to today's gasoline and diesel-fueled vehicles, batteries would have to sustain a single charge for up to 800 kilometers. The development of these super batteries would allow us to harness a greater amount of clean energy, capturing it when it's cheap and abundant, and using it when and where required, possibly enabling us to power larger appliances in our homes and offices, or even large-scale industrial vehicles and equipment. A super battery that packs 5 to 7 times more punch than what we have today would be transformational. What will it take to produce such a battery by 2030?
Well, that's the overview. So let's now hear from Bill Rosehart on how we increase the use of that precious resource, electricity.
Thank you. Good morning. Happy to be here today. So today I'm talking about smart electrical grids. And to give some context to this conversation, let's go back to the 1880s, where Edison and Westinghouse were duking it out over whether an electrical system would be based on AC power or DC power. And we all know today the winner of that in the short term was Westinghouse. We have an AC power system. However, if we look at our computers and most of the gadgets that we run around our house, DC is starting to make a resurgence. But since then, there really hasn't been a fundamental change in the way electrical power systems operate. We generate electricity largely in centralized sources, big hydro dams, big coal power plants, nuclear plants. We ship electricity through a massive grid of transmission lines. The electrical power grid in North America is considered by many to be one of the most complex systems we have ever built. And then finally, we have load, which is really the consumption. And if you look at the basic principles of how we operate our electrical power system, it's the load that dictates what happens. You walk into a room, you turn the light switch on, you expect those lights to turn on. Yet somewhere in the system, there's a generator that has to respond. You go home, you turn your oven on, we don't think about it, but somebody at a generating station has to increase the amount of power, whether it be water falling down a hill or whether it be shooting more coal into the coal generator, coal-based generation. Somebody has to respond to that. We have to have balance instantaneously. So since the 1880s, things haven't changed. You turn the light switch on, you want it to turn on. The transmission and the generation have to respond to whatever the load wishes. With smart grids, everything's going to change. Everything can change, and that's going to become a real enabler for making real progress in our emissions and greenhouse impact. So to have a context of what power systems have to deal with and look at, I'm from Alberta, University of Calgary. The green line is what the load profile on a typical day in January looks like. It's actually fairly flat, meaning we don't see a lot of variation in the load. And that's a real challenge if you want to integrate something like wind, because we all know wind or solar, for example, it varies. Ontario, much bigger system, you do see more of your typical variation where you see that peak happening around dinner time. One of the differences between Ontario and Alberta is residential, you and I, in Alberta, assuming you were in Alberta as well, it only constitutes or makes up about 20% of the load. Alberta is a very industry-heavy province that tends to have more 24/7 type of load profile. Another way to look at the distribution of the loads, so you have an idea of what we got to plan for, is to take the load in each hour of the year and then sort them from highest demand to lowest demand and put that on a graph. And that's what I've done here. And again, you can see the green line in Alberta, we have a fairly flat load profile. Not a lot of variation from the highest demand in the year to the lowest, where you see a fairly large variation in Ontario. Now, from a power system planner, Alberta's great, especially if you like coal or nuclear, because those are two technologies that they like. If you own those generators, you want to turn them on, and you want to keep them on, and you want to have them on at full blast, full power. You don't want to deal with a lot of variation in there. So inherently, Alberta's a place where you're going to have trouble integrating renewable energy, especially wind. Your best case scenario for integrating something like wind is you have a wind profile, meaning the wind is blowing strongest when the load is highest. So if your wind, just by the profile that you're in, follows the load, or we can do something with the load so it follows the wind, you're in your best case situation. And Ontario was probably a better example of that, if only you had the wind of Alberta. So what are the game changers? There's been a lot of game changers in the last decade in the electrical power industry. Wind integration is huge. It represents great potential. Solar at grid level is also becoming much larger. Storage, as we've heard of, and will continue to hear of, is very important for the integration of wind, though the amount of storage will be decreased based on how we can better utilize our own usage patterns. Nuclear will have a role to play. Carbon capture, hybrid or electric vehicles are a game changer in a good and a bad way. They're great in terms of less gasoline. But if that gasoline is being replaced from coal-based electrical generation, the benefit is not as great as one might realize. Locally, it seems better, but we do have to keep in mind what's at the other end of that transmission line. And smart grids, what I'm speaking about today. Smart grids is really a system of systems. We're talking about two-way communications. So instead of just coming into my house and turning that light switch on, there might be some indicator to say, well, maybe I don't want to turn that light switch on, or maybe I don't want to do my laundry right now, or maybe I want to cook my dinner a half an hour later. But what we got to do in the context of the discussions this week is make sure smart grids aren't, well, as Wilson says, they got to be the genius grid. They got to be a lot more than telling us what is the cost of electricity today. They got to do, they can and should, and we got to make sure they enable a revolution in the way we operate electrical power systems. Here's a poster with respect to Korea's smart grids planning. The first thing on the list is the reduction in greenhouse gases. And that is the right way to see it. Because with smart grids, we can enable renewables unlike we can in the traditional power system. We can actually put some control on the load. So there we go, integration of solar and wind. So imagine this. Imagine be given the opportunity, if you live in a region with a reasonable, rich resource of solar and wind, that you could make a decision that you want your electricity to be from green sources. And I know right now you can sign up and you can say, well, 60% of my energy is from green sources. But what that means is over the course of the year, the company that you partner with will buy that amount of energy. It doesn't tell you what's happening in the real time. In the real time, you're getting what's available. In a smart grid environment, where we can push the boundaries and get renewables up to 40, 50, 60, even maybe 80% with the right storage capabilities, you can actually say, you know what? If the wind's not blowing, I'll wait a couple hours to do my laundry, or I'll cycle my air conditioning a little bit differently. And that's integration. Reduction. The simplest thing you can do with smart grids, if they can respond fast enough, is you can decrease the amount of transmission lines you need. But then you got to get the reliability of the communication system just as strong as a piece of wire. All right? In the sense that if something happens in the system, and the signal is we got to reduce the load so we don't have a cascading blackout effect. If you have that spare wire there, that spare transmission line, you're fine. If your communication system fails, you can get a rolling blackout. But smart grids done properly will enable a reduction in grid expansion, which is very important because in North America, we're getting to a context of needing more transmission. An enabler of electric vehicles. If everybody went out today and bought an electric vehicle and plugged it in at 6 p.m., we're in a lot of trouble. All right? So if we all want to drive electric vehicles, and this is my picture of myself in a Tesla, a very fun car to drive. That was a great opportunity. We need to have smart grids. And believe me, just for the fun of driving that car, you want smart grids. Signals to consumers is really the most basic thing. Is to tell us, price of electricity is high right now. Okay, maybe I'll wait a couple hours, but we need it to be more. We need to provide information about what's happening in terms of carbon, the generation portfolio that's on. Is it a lot of coal right now? Okay, maybe I'll hold back. Maybe it needs to be automatic, as I spoke to earlier, that I'm only going to do my laundry when the wind's blowing, so I can make decisions. Or I will allow the air conditioning in my house, and I live in Alberta. I don't have air conditioning. I'm lucky if it breaks 10 degrees Celsius in the summertime. It didn't break 30 once last year. But in Ontario context, allow your air conditioning to vary depending on the availability of renewable resources or prices. So challenges, I already spoke to. It's the reliability of the network, which is going to be driven by communications. New electrical meters, that's important. We got to get the meters right now, because it's not I need a new computer. I've had this one for 2 years. Okay, my computer's 5 years old, but nevertheless, when you put an electrical meter, it's going to be there for a long time. So we got to get the planning done now, and then we got to change the expectations of consumers. Pictures, credit where credit is due, and thank you very much.
Thank you, Bill. That certainly was an insight into the system we take for granted, isn't it? System of systems. Maria Skyllas-Kazacos will now tell us about the promise of large-scale storage.
Thank you, Wilson. And thank you also for the opportunity to the organizers for inviting me to this summit. It's been a great experience for me. I'd like to actually challenge some of the things that Bill was talking about, because it was talking about the fact that, if we want to increase the amount of renewable resources on the grid, that we might have to wait until the wind is blowing before we turn our air conditioner on. Well, that's not what we really want to do. And if we, in fact, have storage, that gives us now the opportunity to use electricity whenever we want it, and even renewable electricity when we want it, because we can actually store that electricity from the wind farm, from the solar farm, from the power station, and put it into a big storage system, and then have it available to be used when we want it, not when the wind is blowing. So that's the importance of storage. And I think it's taken a long time for government bodies and regulatory bodies to realize that storage is actually going to be an essential element of the smart grid. So if we have the smart grid of the future, it's not just about us waiting for the wind to blow or whatever. We can make those decisions. But of course, storage introduces an additional element in the smart system. It's going to cost us something. But again, we have to be prepared to pay for something a little bit more if we want the convenience. So with storage, we can actually put the storage system close to the wind farm, close to the solar farm, near the power station, but we could also put it closer to the load. So there is an enormous amount of flexibility, potentially depending on the type of storage that you use, where you locate it, and in fact that also gives you additional security for the delivery in case there is a problem with the transmission lines, that you still have some storage capability close to the load so that you don't actually have these serious blackouts that can happen from time to time. But so there have been, and in fact we are already aware that there are a number of different types of storage technologies that we use already in certain parts of the world. Pumped hydro is one type of storage, and pumped hydro systems are systems that where we can actually pump the water up a hill and store it, and then when we need the power to actually let the water flow down the hill, where we can run turbines and generate it when we need to. But that sort of storage technology needs you to have a hill, and it needs you to have a reservoir at the top of the hill and at the bottom of the hill to move the water up and down. So it is geographically limited. So we can't put it anywhere. Compressed air storage is another alternative where we can actually pump air into big caverns underground and then release it when we need to generate the power. But again, that requires certain geological formations to exist. So again, there are geological limitations to that type of technology. But it does serve an important role for very large scale gigawatt hours of storage. So electrochemical energy storage. There are many other types of energy storage systems, but in my very short period for this presentation, I really need to focus, and I'll be focusing on electrochemical systems, which are pretty much batteries or fuel cells. The advantages of electrochemical systems is that they allow direct conversion of the chemical into electrical energy. So that means that you can actually have very high efficiencies. A lot of mechanical or chemical type systems have many different steps in the process, so in the end you might only get 30 to 40% of the energy that you put in that you can actually recover, and that's not what we really want. So, but with electrochemical systems, you can get 60, 70, 80, 90% of the energy, depending on the technology. You can get it back again, and that's very, very important. They're also modular, so we can actually have them. We can make them small enough to put them near a house or a small, an apartment block, or we can make them slightly bigger and put them into substations, or we can make them even bigger and put them into integrate them into a wind farm. They have very short construction times, so it doesn't take us many years to plan, to get the approvals. A very short turnaround time for the installation. As I mentioned before, they can be, because they are fairly clean. Most of the time they are quite clean. You can actually put them very close to residential areas without any problems as well. And they're not limited by geography or geology. Relatively low cost, low maintenance as well. There are many different types of batteries, but I can only really talk about one, and that's the technology that we've been working on for many years, which is the flow battery. And many studies have already been done that show flow batteries actually have the potential to provide very low-cost, high-efficiency power for large storage capacity, especially the types of storage capacities that are needed for renewable energy storage. So I'll talk about, as an example of a flow battery, I'll talk about the vanadium redox battery, which is what we've been developing at the University of New South Wales for many years now, actually. But it started off with a concept that was proposed by researchers at NASA back in the 1970s. One of the problems with that particular, the NASA technology, was that the chemicals that they chose were two different elements, of chromium and iron, on each of in each of the half cells. But basically how it works, it stores energy in a solution. So it is electricity in a bottle. And that's what one of the earlier presenters said, wouldn't it be nice if we could actually store electricity in a bottle? Flow batteries will actually allow you to do that. Although it won't be a bottle, it'll be very large tanks. But these are in our case, we use vanadium. We use two different forms of vanadium, one in the negative half cell and one in the positive half cell. And actually, when those solutions undergo charging and discharging, they change colours. So here you can actually see the different colours of vanadium, which are absolutely beautiful and spectacular. And in fact, they even give you a visual indication of how much energy you've got in your system just by looking at the colours. And so that's a really good, it's a cool sort of thing to play with. But a flow battery has a cell stack, which is like the fuel cell stack, which is like the motor, which determines how much power you can generate with the kilowatts. But there's total flexibility in terms of how many hours hours you can generate those kilowatts for, whether it's 1 hour or 2 hours or 10 hours or 20 hours, simply by adding more solution, bigger tanks. And therefore, and that's very important because that means that as you to increase additional capacity, the cost per kilowatt hour of extra capacity that you install is quite small. So the cost per kilowatt hour for large storage times drops off quite dramatically, as shown by this graph here. And that's very important because when we're looking at renewable energy systems, which require perhaps 6, 8, 10 hours of storage capacity, that potentially becomes the cheapest type of storage technology, the flow battery. We've already had, over the last 15, 20 years, we've already had quite a lot of demonstrations of the vanadium battery, mainly by Sumitomo Electric Industries in Japan, but this is one of our very early demonstrations in Thailand, where we installed a vanadium battery in a solar house, which had a 1 kilowatt module on the roof, and this was meant to be grid connected, but to try, and the grid was used as the backup power system, but the idea was to actually integrate the battery into the house so that you can make the house energy self-sufficient. And the important thing here was cost is often regarded as an important consideration, but in this particular case, the company that was proposing this design was talking about integrating it into the house, so the cost of the solar and the storage didn't really become an issue because it was part of the total package and the cost of the house. And I thought that was a really smart idea. There have been backup power demonstrations. This is one system which was installed in a factory to provide backup power in the case of blackouts. And that in that particular case, it managed to save quite a lot of. There was a payback period of 6 months just from the saved capacity or manufacturing production losses from that. From those blackouts. Load leveling is where we use the excess capacity. If you have a very large difference between off-peak and peak requirements, you can use those periods at nighttime to charge the battery and then offset the peak demands during the daytime. And there have been a few demonstrations in Japan showing very high efficiencies, 80% efficiency for the round trip. Wind storage has become a very important situation and application because we're seeing a lot, in many parts of the world, we're seeing a lot of wind farms being installed, but they're creating a huge instability to the grid. But by having storage, we can actually shift that load, but also smooth out those very short-term, high-frequency variations, fluctuations. And this is one demonstration in Japan by Sumitomo, which installed a 4 megawatt, 6 megawatt hour battery. And it actually, after 3 years of operation, it had undergone 200,000 cycles, which is, again, very, very important when you're looking at wind, trying to stabilize wind turbines. Cost is very important, as I said, and this is some calculations that we did where we compared vanadium flow batteries with what is currently the cheapest type of battery, which is the lead-acid battery. When you're looking at storage capacities above 2 to 3 hours, vanadium flow batteries or flow batteries become much more cost-effective. Transport, something for the future. Although the energy density of the vanadium battery is very small, or the flow battery is very small, it does give you the opportunity to consider the possibility of actually refueling, where you can actually drive into a refueling station during the daytime, anytime you want, exchange solutions, and then pump in and just fill your tank with electrolyte. And then overnight you can recharge the batteries when you've got cheap electricity available. So this is my vision for the future, where we have buses or trains or other sort of public transport using vanadium batteries where you can refuel any time, where we have solar panels on our roofs, or we can have batteries in at the local substation, and we use a large quantity of renewable resources for most of our electricity needs. Thank you very much.
Thank you, Maria.
Thank you.
I'm done. Thank you, Maria. It sounds like it's quite exciting. It's been sitting there and we haven't even known that they're actually in production. Ted, you're going to give us some ideas for solar cells.
Well, thank you. Our energy utilization is vast. 15 terawatts of power are coursing through the global grid right now. What the sun is providing the Earth right now is almost infinitely more vast. 120,000 terawatts, 6,000-fold, typically more energy is reaching the Earth from the sun right now. There's this vast excess of energy reaching us from the sun relative to our already vast needs. To what extent are we satisfying those needs using solar energy today? Our solar production, compared to our utilization of all energy sources, is puny. It's tiny. Why, with this huge energy need, this huger energy resource, is our utilization of this free, clean energy source so fractionally low? It comes down to cost. And when we think about cost, we'll never think about it in isolation. We'll always think about it in combination with efficiency. It's a dollars per watt peak of production. Today, systems are $2.50, $3 per watt peak for the very lowest cost systems available. That corresponds, when you think about bringing the capital cost of the system from the future into the present, to what's called a levelized cost of electricity of about 15 cents per kilowatt hour. Doesn't seem too bad, but it's probably more than most of what you are paying for your electricity at the moment. A lot of the graphs that I've borrowed to introduce this topic are taken from a US Department of Energy study, which sets an ambitious target, a target that is not yet reached. In fact, there's not even a direct path to it, to get down to $1 per watt peak. That would correspond to a levelized cost of electricity of 5 cents per kilowatt hour. Why is that a worthwhile goal? What would that do? On the left is a reference case of what photovoltaic or solar producing energy utilization would look like in 2030 if we just extrapolate based on kind of existing technologies and cost reduction strategies that we have today. On the right, you can see what happens to the map of the US if instead we have a breakthrough, if we achieve this vision of $1 per watt peak. All of a sudden now, it's not just people living in specific jurisdictions with particular energy requirements or who are harder to connect to the grid, or it's not just jurisdictions with very high electricity prices. It's not just people who really care about the environment. It's even purely economically rational, self-interested actors who go solar in 2030 within this visionary scenario. What does that do when they go solar? Well, instead of, in the reference case, based on extrapolations of today's assumptions, about 1% of US energy production being from the sun in 2030, in the $1 per watt peak case, 14% have gone solar. One of the impacts of this is a reduction of 200 million metric tons of carbon dioxide equivalents relative to the reference case. So we're a ways from this goal. I mentioned this earlier, that the cost per watt peak is now in the multiple dollars, depending on the technology, but no existing solution offers today this $1 per watt peak vision. And it's really important when we think about cost to recognize that one cannot simply say, if I can make a solar cell that is cheap enough, then I can correspondingly reduce my expectations on the efficiency of it. I want to persuade you that, in fact, this breakthrough is all about improving efficiency while maintaining the lowest available costs. So if I include the balance of systems, so the costs that aren't in the module, but the costs related to the land, to the installation, to the price of money, bringing that money from the future into the present, then if I make a 10% efficient cell and I want to achieve $1 per watt peak, then I can sell it for nothing. I have to give it away for free. I can't make any money. I can't even pay back my costs to make it. But if I make a 15% efficient cell, I can charge $50 for it. And if I make a 20% efficient cell, I can charge you $100 per square meter for that cell. $50 to $100 per square meter is demanding. It's tough. It's not what we can do today. But when you think about technologies like printing a newspaper, making flexible fabrics, that sounds reasonable. So we need techniques that simultaneously achieve breakthrough efficiency and breakthrough cost. We can't have one or the other. So flexible photovoltaics offer in principle this path to these low costs per square meter. But there's this urgent need for this greater efficiency that I was alluding to. And to think about the potential for greater efficiency, we need to think about the sun itself. On the left is shown the sun's spectrum. The transition from the visible to the infrared spectral regime occurs around 700 nanometers. If you integrated the area under the curve to the left and to the right of 700 nanometers, you'd find about equal amounts of energy on each side. So you'd find about the same amount of power in the visible and the other half of the power from the sun residing in the infrared. A lot of the lowest cost technologies available to us today only capture the visible portion. They leave the infrared half on the table. So clearly, addressing the sun's full spectrum is going to be key to our reaching the upper limits of efficiency that we will be required to meet. On the right graph is a further comment on the importance of spectrum. The fundamental upper bound on harvesting the sun's energy at what's called one sun, so without using concentration, is about 30%. If we only use a single type of semiconductor having a single band gap, a single set of spectral properties. But if we can make a rainbow solar cell, one that treats every photon as special, one that first harvests the visible, and then the near infrared, and then the short wavelength infrared, gets the juicy photonic energy out of the abundant energy contained in the visible spectrum, and then mops up the abundant current of photons at the longer wavelengths, we can achieve higher reaches of efficiency. Our upper bound is improved through better spectral utilization. So there's an urgent need for full spectral utilization and for treating every photon as special. My research group at the University of Toronto works on this problem using a class of materials called quantum dots. This is a transmission electron micrograph of these. Each of these particles that you see is very similar to the others. They're almost identical to each other. And in this picture, they're about 10 nanometers in diameter, each of these particles. We were able to synthesize these on a very large scale, trillions and trillions of particles in one synthesis. We're able to synthesize enough of them to paint the wall, a square meter of wall with $10 or $20 worth of materials. Costs are very low. They're synthesized and they're processed from the solution phase. Quantum dots, the quantum refers to the fact that we're able to manipulate the properties of these materials using quantum effects. This is a picture of a wave. We all know that if you take a guitar string and you shrink it down in its length, you can change its resonance frequency. Well, because electrons are quantum particles, they're waves as well as particles, when we confine those electrons to a smaller size, we change their resonances too. And so with quantum dots, we have a tunable material. Tunable only because the material is configured at the nanoscale, the scale commensurable with the characteristic electron wavelength. And so we can make rainbow materials. Using a single precursor, a single starting point, we can make a rainbow of colors for absorption or emission of light. In my group, my graduate students discovered about 6 years ago that we could make these materials, incorporate them into a polymer, and make a solar cell that captured the sun's visible and its infrared light. The solar cell also evinced the spectral tunability of the particles that we used within it. The sensitization, the light absorption came from the particles. They transferred their energy to the matrix. We were able to extract that energy in the form of current and a voltage. So we had the first hints of the potential of a full spectrum solar cell. And what we've been working on in recent years is in trying to get that efficiency to higher and higher reaches. We haven't yet met our goal. We're not even above the 10% efficiency yet, which is really the starting point I described for potentially having something compelling. What we've done in the last 5 or 6 years is we've managed to achieve efficiencies comparable to what organic solar cells offer, and we think that we're nowhere close to running out of steam. There's the upper bound on the potential for efficiency that we can achieve in principle is very high. For a single junction cell, it's 30%. We have a lot of runway to meet the full scientific potential of the technology. When we start making tandem and triple junction solar cells, cells of different band gaps stacked on top of one another, rainbow solar cells, then we will be reaching towards upper limits of 40 or 50%. So we have a huge amount of engineering runway left to perfect our approach, to perfect our material system, to make full use of the sun's spectrum. In fact, these grating properties, the fact that these quantum materials allow this tunability, it can be used not only from cell to cell to cell, from junction to junction to junction, but we found recently that even within a solar cell, we can create a waterfall, a cascade, that propels electrons towards where we collect them. So we're able to use quantum size effect engineering in these nanomaterials in order to make the cells themselves more internally efficient. It's not just about moving the electrons around, it's also about light. And this will sound very green. We have an initiative on photon recycling, where we try to make the very best use of every photon coming in. For even a very thin amount of material in these thin film solar cells, we're able to increase the absorbance by enabling light to propagate not just into the material, but along the structures. And we do that by engineering the structure of the surface now not on the electron length scale, but on the photon length scale. So this idea of commensurability, of engineering on the length scale of the particles that we're trying to manage, in this case photons, rises again when it comes to managing light. Ultimately, the dream is to be able to get materials that self-assemble into novel structures. And we've recently managed to show that these quantum dots can actually be assembled in solution into larger scale structures of multiple quantum dots in a very controlled fashion, like is shown in this illustration. We think of this, people often talk about these quantum dots as artificial atoms because they kind of define their new periodic table through their tunability. And what we've done here is made the first steps towards building artificial molecules out of our artificial atoms. These artificial molecules have the capacity to act like antennas, a bit like the photosynthetic apparatus in a leaf, to funnel energy towards the central atom within our molecule. So it's really designer matter, designer materials towards our purpose of achieving low-cost, high-efficiency energy harvesting. So that's what we need. We need to not have a compromise. We need to simultaneously achieve efficiencies that are reaching up towards the best of what can be done today using incumbent technologies, combined with costs, simultaneously combined with costs that align with those of the lowest cost technologies available today. The efforts underway in our group include making full use of the sun spectrum, using solution process nanomaterials for low cost and physical flexibility and deployability, and also making the very best use of the photons and the photon recycling concept. Thank you.
Thank you, Ted. Thank you, Ted. Treating every photon as special. I quite like that. Now we're going to hear from Walt Patterson, who's going to tie it all up in ribbons for us, isn't he?
As you've heard, we've already started transforming electricity, but we have a long way to go. The resources are there. We can enhance generation, performance, and infrastructure altogether. Indeed, that's the way we need to approach this transformation, as a complete package. We should be aiming at a complete new concept of electricity in society, a transformation of the whole system. That's the first and most difficult transformation. We have to change the way we think about electricity. Then we have to change the rules accordingly. We've come to think of electricity as a commodity. We've come to believe that what matters is an electricity market, commodity trading in kilowatt hours, short-term batch transactions in which the unit price per kilowatt hour is the key. Electricity is not a commodity. Electricity is a process. It's a process in technology, and what matters is the technology. What matters most, moreover, is not the electricity generating technology, nor the delivery network. What matters most is the user technology and user infrastructure, the buildings, the most important energy technology of all, the buildings, what's in them, the fittings and appliances, lamps, motors, electronics, and so on. The technology that actually provides the electricity services we want: comfort, illumination, motive power, mobility, information, entertainment. We keep hearing about problems of energy security and climate. These problems are not about energy. They are quite specifically about fuel. We seem to have almost forgotten the word fuel. When politicians worry about what they call energy security, They are really worrying about supplies and prices of hydrocarbon fuels, particularly oil and natural gas. The main climate problem is the effect of using fossil fuels. If we want to reduce our vulnerability to disruption of fuel supplies and climate, we have to reduce our use of fuels. When we talk about a low-carbon future, what we really mean is a low-fuel future. We hear a lot about competition as a way to get the best energy services. What we need to understand is that the key competition is not between different suppliers of fuel or electricity. The key competition is between fuel and technology. The better the user technology, the less fuel we need to get the service we want. We need to shift the balance away from fuel toward technology. We can do this in two ways. First, we need to upgrade the performance of our user technology and user infrastructure, and especially buildings. We know how. We've known how for decades. But we've hardly spoken about that at this summit. We need to get serious about it. Reducing energy waste should be our top priority. Then, we need to realize that we use two kinds of electricity. One kind we generate from fuel, such as coal, natural gas, or uranium. The other kind we generate by using technology and infrastructure to convert natural ambient energy, sunlight, wind, waterfalls, into useful electricity. Most people call this renewable. I call it infrastructure electricity. Infrastructure electricity does not use fuel. Performance upgrades and infrastructure electricity go hand in hand. Both require mainly upfront investment with minimal subsequent running costs. Both are completely different from what today's politicians call the energy market. What we need is not short-term batch transactions, but a market in long-term contracts, forming long-term business relationships and creating the jobs that produce the physical assets, the high-performance user technology, and the infrastructure electricity to run it. As Bill says, traditional electricity is based on a technical model which is now more than a century old. It is overdue for transformation, starting with generation. Before climate became an issue, I spent much time and effort advocating advanced coal technology with very little success. Coal producers were utterly uninterested. Now I have to concede that we had better phase out coal worldwide as fast as possible, or we'll have no hope of preventing climate catastrophe. At one stage, I thought carbon capture and storage might alleviate the problem. Now, I'm deeply skeptical, because it depends on staying with traditional electricity instead of transforming electricity itself. People ask, do we need nuclear power? To me, that's like asking, do we need a broken leg? If you're really serious about climate, and you'd better be, why pick the slowest, the most expensive, the narrowest, the most inflexible, and the riskiest of all the options to put your political weight behind? By riskiest, I used to mean in purely financial terms. That's why private finance will not finance new nuclear power plants without open-ended guarantees from us taxpayers. Now, however, Fukushima has reminded us that nuclear risks are not just financial. Nuclear power, to me, is a dangerous distraction, traditional electricity at its worst. Natural gas, on the other hand, is a valuable partner for innovative infrastructure electricity. Natural gas generation can come in small, rapid increments, right down to on-site generation, cogeneration, and trigeneration. It helps to foster the essential change in electricity networks. Traditional centralized electricity needs radial one-way networks. They carry large electric currents long distances from huge, remotely sited power plants to much smaller user applications. Innovative electricity will be much more decentralized. It will have meshed two-way networks, linking many more, much smaller generators, much closer to applications of broadly similar sizes. All parts of the system will be heavily instrumented, communicating with each other continuously in real time. We may not even be involved. People wonder what sustainable electricity might look like. It won't happen by 2030, but I think eventually sustainable electricity will be invisible. Not just invisible as it already is, but invisible to any so-called electricity market. Suppose, for instance, you have an office building with a photovoltaic skin and low-voltage direct current cabling to drive its high-performance LED lamps, its computers, its motor drives, and all the other direct current appliances we already use. If your own building is powering your appliances, you won't need to meter the direct current, any more than you meter the DC flowing through your BlackBerry. Infrastructure keeps the lights on. Let's change the way we think about electricity and change the future for the better. Thank you.
Fabulous, Walt. Well done. Well done. Well done. Bit of a challenge there for all of us. Thank you, Walt. Okay, we're going to go in a quick discussion and then we'll go to questions from the floor. First, Bill, there are some major problems with today's power grids. Well, problems, opportunities, shall we say, to enhance it. What kind of things can we do with optimization and distributed generation?
So I should qualify, because all the power engineers I work with will want me to start by saying the grid itself, there's not a major problem with it. As we heard, the problem that we're primarily facing right now is the fuel. And so in terms of optimizing, we really need to look at an integrated approach to it in terms of distributed generation, centralized generation, and we need to optimize to find the right blend that is sustainable. And it will be a mix of a lot of technologies, certainly in the short term. And when I'm speaking short term, I'm talking 10 to 20 years from now. So different terms for different people in terms of short. If in 10 to 20 years from now we have 15, 20, 30% penetration of wind-based generation or solar-based generation, we're doing very well. We certainly will look at increasing distributed generation. It could be natural gas. It could be a combination of heating plus electricity in your homes. The one challenge, of course, with natural gas is uncertainty around supply, although we're quite abundant with it right now, but it does lock us into a particular technology in the long term that is fossil fuel based. So optimizing to me is bringing a blend of solutions together, and distributed generation is certainly one of those.
But there's also, it's not just meters. When you talk about a smart grid, it's not just meters in your house, but it's also having the electricity cycling both ways, isn't it?
Absolutely. That's one of the, as was said, we at the transmission level, so that's the bulk power of electricity, we don't have a radio system, we have a grid system. In a lot of jurisdictions, for example, Chile, it tends to be sort of a flow in one direction, but if you take a location such as Spain, it really looks like a cobweb, the electrical power grid. And different systems look differently. When it comes to smart grids, we are going to see power flowing in multiple directions. It could be that your house is, the wind is blowing in your house and you have a turbine in the back. And we have people that are working on efficient, small-scale electrical turbines. In that case, power is flowing a different way. The system right now is not designed to handle that. And we need to, if we're going to go down that road, we need to be prepared to make the changes, but they won't happen overnight. Even from a very simple safety perspective, the safety for the people working on the electrical systems are, if an electrical pole falls down, it's all set up assuming power is flowing one way. So we can't just expect utilities to change instantly. And we have to understand that there are some technological challenges. They can be overcome, but they do take time. And so when we're planning now, it's really important to have a picture of where we want to go in terms of the blend and the sustainability. So as new neighborhoods are built, they're built with the infrastructure to enable the technology of 10, 15, 20 years from now.
Start from scratch. Maria, it's a very attractive picture you paint of storage as being something that you can have in your house, you can have in your in the grid, in a building. Would it change? It would change the way we use energy completely, wouldn't it?
Well, that's the whole point of storage. It gives us the total flexibility. We're not reliant on the wind blowing, the sun being there in the daytime. It's going to be there in the daytime, but it's never going to be there at night. But the clouds come over all the time. We never have a totally blue sky. So it gives you that total flexibility, so you don't have to rely on all of these uncontrollable events in nature.
But would it mean that a building could draw down the power it needs and then release it during the hours, maybe when it's off peak?
Well, exactly.
Buying cheap power.
And even if you don't have renewable energy on the grid, there are many places where there is a big difference between the peak and the off-peak load profile. And in Sydney, for example, because we have already got smart meters in many houses, not necessarily smart, but the way they operate is that they try to encourage us not to use electricity during the peak times, which are 2 p.m. to 8 p.m. In the daytime, which is when everyone's using most electricity. So because during that time, we have to pay 40 cents a kilowatt hour, whereas between 10 o'clock at night and 7 a.m., we can pay only 10 cents a kilowatt hour. So that, when we were forced onto this new smart meter about 3 or 4 years ago, we did change the way we use electricity. We shifted a lot of our load at nighttime. And in fact, we found that we were saving on our electricity bill. But with storage, you don't really need to try and shift your lifestyle. Of course, it is good to try and reduce your consumption anyway, but we don't have to change our life in order to satisfy the...
But I can see a world, following on from what you said, Bill, I can see a world where if the price is fluctuating depending on demand and use, then you can have an automated system in the background only buying power when it's a particular price and storing that and then bleeding it out through the rest of the day. So it's quite attractive.
Yes, definitely. And I think that's really, there are so many opportunities right now, just with the way we currently generate power, but also in the future, if we're going to use more renewable energy, that becomes essential then. We really need to, because the wind there is so much fluctuation and it produces so much instability to the grid, and we just need to have storage. If we're going to go more than a few % of renewables on the grid, we need to have storage.
I love the sound of your quantum dots and the way that you treat photons, very respectfully. Are there any really out there ideas can really push this even further?
There's some very exciting stuff in the works. So I spoke about making kind of a multi-layered or a laminated structure that treated every photon as special. Well, there's people around the world working on making a single layer where a highly energetic photon comes in and generates 2 or 3 electrons. And so within a single layer, without needing to employ the lamination strategy, there's a gain or sort of a multiplication effect. The phenomenon is known as multi-exciton generation. And there's tremendous interest in that around the world. Another area that I think
you're getting more power, more light from
the
same...
higher, essentially reaching a higher efficiency, ideally reaching an efficiency that is not limited by having a single band gap, but reaching into those higher reaches of efficiency that I showed on my bar chart that normally would be achieved using a stacked structure, being able to do so within a single layer, which would provide a simplification.
So we could have buildings with this stuff.
That's the vision, and in fact, that's one thing I didn't get to talk about. But I mean, my picture of balance of systems cost is I think is a worthwhile one, isn't a simple one, but it didn't allow for the fact that there are different balance of systems costs, right? So when you do, as was being suggested, when you build a building from scratch and you're just using building materials that are also solar cells, some of your installation costs or your delta in installation costs can be reduced because you're already installing those materials in the first place. And so that's a nice thing for people in the solar ecosystem, in that there are early adopters available to you as you ramp up your production and as you build a new technology and deploy it.
Bill, you gave us a bit of a shock there. You know, you're really getting us to think about efficiency, which is fair enough, because we have been looking at sorry, Walt, my apologies. We have been talking about how we increase the amount of electricity we generate and how to deploy it, but we haven't been talking about reducing it. So I think it's a valid point. Is it just buildings, or is a whole cultural change required?
I think it's a whole change of mindset, and particularly on the part of people who actually are making the decisions about these technologies, these finances, these institutions, that we really need to, so to speak, start from scratch with a clean slate. If we were starting now to design an electricity system for the planet, using what we already know technologically and financially and even sociologically, it would look utterly different from what we have at the moment. But at the moment, what we have, the so-called legacy systems, are what keep our lights on. They're what keeping the lights on in this room. So what we have to do is an evolutionary process. We have to change things sufficiently gradually that we don't black ourselves out, but at the same time anticipate where we would like to be 50, 100 years from now. Not just 20, but 50, 100 years from now. Because if we have some sort of vision of what we think an acceptable, sustainable future might look like for our grandchildren, then that will give us at least a sort of benchmark to decide whether the decisions we're making today are actually taking us in the right direction.
That's fantastic. Thanks, Walt. Our discussions in the summit have centered on technologies and innovative approaches, but we've also had innovation from our talented forum of future leaders who have been helping us to critically evaluate help and develop approaches to making these technologies and ideas a reality. So let's open the floor to the forum and hear some of their questions on today's session.
My name is Jose Maria from Mexico, member of the forum. I really like today's presentation because we're moving to other sectors. We're moving, in these cases, to construction and building sector, which are so active in developing countries. Now, if we got the policies and the finance and the business models right for all these new type of material construction and all these new ideas, we would have to face the issue that normally people, families invest in their houses or their buildings with mortgages of 20 to 30 years. What's the lifetime of these technologies? Can these technologies cope with this type of long-term process of planning and investment in families' assets?
Can I start with that? Maybe
please do.
So I didn't make this explicit, but I should have. When I was talking about levelized cost of electricity, there's an assumption about how much lifetime that solar cell has. And the assumption built into those models is 25 or 30 years. And it basically has to be in order for things to work for the reasons that you were saying and in order for the cost to be acceptable. And so that is something that existing technologies can deliver, and that is something that incumbent technologies will have to deliver, and they're not doing it yet. And so whereas I talked about efficiency as king, and I do think that's the first step in the coronation, it's clear that reliability is also absolutely crucial on the kind of 25 to 30-year time scale that you mentioned.
Zoe, you have a question.
Could I just add something?
Excuse me. Yes,
no, I just wanted to add something about the batteries and storage. And one of the things that always amazes me is that people expect these technologies to last forever, and yet everything that we have in our house, we have to maintain it. You know, every few years we've got to paint the house, we've got to maintain our refrigerator or our air conditioner, and this is the same sort of thing with any energy storage system. You've got to build in some sort of maintenance cost, and it could be every few years that you have, someone comes in and checks the system and then just does a very simple maintenance. So these are things that are factored in, but we are working towards a sort of 20-year life with periodic maintenance.
Sorry.
So the idea of a smart grid really excites me, and perhaps it's mostly because, and correct me if I'm wrong, but I assume it would also give us the potential to somewhat manage demand from households or businesses. And I wonder if maybe it's to both Walt and Bill, because we have been talking a lot about how we meet the demand, the growing demand, but do we actually have to keep demanding so much? And would a smart grid really allow us to do something like, let's say, have something equivalent to a cell phone account where you say, oh, well, get a little message that says, you have reached your limit of kilowatt hours for this month. Would you like to increase your account? Something that's bringing really smart technology to how we use our energy and an acknowledgement that you are using more than maybe everyone else is.
Shall I start with that? Let's first of all recognize one of the problems we have goes back to the invention of the electricity meter in 1885. Up until that time, Edison and his contemporaries had to optimize the whole system in order to keep the costs at least manageable, for their very wealthy clients. But once the electricity meter was installed, suddenly the system was no longer selling illumination. Edison originally charged his customers according to how many lamps they used, but he was then selling electricity by the unit. And it was actually in Edison's interests for his customers to have inefficient lamps, because in order to get the same level of illumination, you had to buy more units of electricity. And this crazy incentive, this perverse incentive, is still at the heart of the way we deal with electricity in society. The electricity companies, however much lip service they give to energy efficiency and improving performance and so on, at bottom, what they want to do is sell kilowatt hours. And if we don't change the rules, then that is going to continue to cripple the way we deal with this. What we need to do is think hard about ways to make it possible for big players, big influential players, actually to change their business models so that it starts to become in their interests to help the rest of us upgrade the performance of our houses and our office buildings and what have you, as a profit-making part of their business. So that we can actually, there are now a whole lot of new financial ideas coming to the fore, like so-called property-assessed clean energy bonds in the US, or what the UK government calls the Green Deal, where an electricity or gas supplier can upgrade your building and get a return via the electricity bill, but your bill is lower anyway because the upgrade reduces your bill. So this is the kind of innovation that really needs to be thought about, not just technical, but institutional and financial innovation. And then, as you say, we will be able to start thinking seriously about reducing the amount of electricity we use as an active business proposition and as a contribution to the economy, as well as to the environment.
We have a question in the front.
Hello. It's actually related to, sorry, my name is Geeta, I'm with the forum as well. It's actually related to the question of smart grid. It's been one of the main benefits that is actually being offered by smart grid, and that's why the developing countries such as Pakistan, India, China, Indonesia is opening their door, is actually, first, you can sort of manage or control the energy demand, and second, you could prevent power theft. But then again, the people that are actually already moving forward to it, which is the developed world, now you can find website with like www.hackyoursmartmeter.com already, and like there's public video that you can access, and you can actually temper your meter to actually underestimate your usage. And I would imagine in countries with like developing countries such as my country, with very creative way of thinking, in that sense, it could even grow to a bigger business where people could open a business to, okay, let's, I can hack your meter when you pay me a certain amount, and is it actually worth it when it's actually money that you can invest into something else, judging from the very high cost?
That's one way to reduce electricity costs.
So I get the creative question. So if I was going to be creative, I would bypass the meter altogether, in which case it doesn't matter what meter you have there, and I'm going to do it anyways. I do feel smart grids will play and should play a very important role in the future. And to go back to the previous question, and there is a connection there, we got to remember when you're planning and operating electrical power systems, you're dealing with different variables on different time scales. And so one of them, with respect to smart grids, is shifting the usage pattern. So if you think about a city, if we think about residential, you have this peak around dinner time, and after 8 o'clock, the demand goes down. So you can use smart grids to shift that over, and you can do that, for example, just by giving a price signal. You know it's going to be 40 cents a kilowatt hour instead of 10 cents a kilowatt hour. It doesn't even have to be real-time pricing. It can be block pricing set up in advance, and that will result in some change. Now, if you're just shifting the usage, so I'm going to do my load of laundry at 9 o'clock instead of 6 o'clock, the energy stays the same. And that goes back to the fuel then, integrates in, for example, battery storage or other technologies. We need to use our system more efficiently. That is bringing down the peaks and flattening the consumption throughout the day. That way you don't build large transmission lines that are being used 20% of the time, or build big generators that are being used 15% of the time. They're known as peakers. But you want to use all your resources more efficiently, and that can be combined with battery power, for example, and other storage techniques. But we ultimately have to come back to that overall energy usage over the year.
Can I add a little corollary to that? It won't happen right away, but one of the implications of thinking about the combination between a smart grid and a smart meter is that at some stage, you may well get to the point where the customer, the user, doesn't have to pay any attention to this at all. It's done by two-way communication between the different parts of the network, between the generation, the network, and the loads, the appliances. That they do this themselves. And so you may well get to the point where the electricity meter as such is no longer of any interest to you, even if you're getting electricity out of the network rather than from your own building. That's a long way down the line, but let your mind expand a bit about some of this, and you begin, if you once get out of the traditional mindset, an awful lot of new opportunities become available.
Leah, you have a question.
From Brazil, and my question is for Walt regarding your feelings related to nuclear energy. In previous sessions, we have seen that we can use the nuclear waste to produce energy. And I would like to know, so as you are against the expansion of nuclear energy, what's your recommendation about to do with this nuclear waste we have nowadays?
Well, if I had a recommendation, the old story is I wouldn't start from here. But unfortunately, we do have a huge and increasingly embarrassing inventory of nuclear waste that's already there. The difficulty with the proposal that was put earlier this week for me is that I think it compounds the problem. It continues, for one thing, it would have to, if it were to be done seriously and were to make any significant dent in the existing inventory, we would have to build an absolutely dumbfounding number of units of the thorium type in order to make a significant impact on the existing very, very long-term inventory of so-called actinides, transuranic radioactive waste. And at the same time, we would be turning some of that very long-lived waste, which is actually, because it's long-lived, it's actually not very radioactive. We would be turning it from a very, very low-activity, long-lived waste into a significantly higher activity waste, which would then have to be managed itself. You know, so you're turning plutonium and neptunium and so on into cesium and strontium, which are themselves problems. So I'm afraid that much as I would like to think that this could be a valuable way to go about it, I'm afraid that the existing inventory is so large that to make a significant impact on it, even if we don't build any new nuclear plants of conventional kinds, we would have to build an awful lot of the others. And as yet, of course, there's still basically a laboratory technology. I gave an interview once to an Italian journalist in which I said that the cheapest reactor is always a paper reactor. And this young lady wanted me then to describe the characteristics of a paper reactor. I had to explain that this was a metaphor. But my difficulty with nuclear technology, which I've always been fascinated by, is that it turns out to be extremely difficult to get right. And we have a very bad track record of not getting it right.
We have a question up here.
Hi, Graham Stemp-Morlock. I'm from Canada and have been sitting in on the sessions and blogging for WGSI. My question's for Bill. When we look at information technology, my cell phone is outdated dinosaur within 2 years. My iPad from a year ago is replaced. What sense does it make to add a smart meter and information technology with a 25-year horizon?
Well, I think it makes a lot of sense in terms of what you're aiming to achieve. And that is the integration of renewables. That is levelizing the demand of the system, bringing information. It can be price signals, it can be pollution indexes to the consumers. But one of the key challenges is the reliability, for example, of your telecommunication system. If the signals aren't being sent properly, especially if you use the smart grid to enhance stability or as a tool for stability of your system, so that you don't build that new transmission line, but now you have an issue that if one of your transmission lines go down, you'll get a cascading effect because you got overflow on your other lines. That's why we have lots of redundancy and lots of lines. But you decide, instead of building that new line, I'm going to use a cell phone signal to the loads to say, turn off. Well, imagine a drop call. That would be a very bad time for it. So it's not so much, to me, the lifespan of the cell phones, because they're relatively inexpensive in that technology. If it needs to be replaced, it can be replaced. To me, the key challenge is going to be getting the reliability that we need if we push the smart grid into removing some of the transmission or even generation infrastructure.
Because it's not just the little meter you have, it's also the stuff in the background that feeds that, isn't it?
Absolutely. It's very much a systems approach. Yeah. Everything needs to work. I know it sounds sort of strange to talk about the reliability of a piece of wire, but if I hold a piece of wire out, it's not going to suddenly disappear. But my cell phone can drop a call. And it's that high reliability of the piece of wire is what we're aiming to achieve. And that's because of our expectations. We have an expectation that the lights will stay on 99.999% of the time, and in some cases more nines after that. And so it does come back to what our expectations are. In different parts of the world, they don't have that expectation. They would be quite happy with 9 out of 10, even 8 out of 10 in some places. But we don't want to see a cascading blackout because of the infrastructure we have. For example, nuclear plants, they don't like being turned off quickly. That's not a good thing. So with the technology portfolio we have in terms of the generation units, we need to keep the system reliable. And so when we move towards smart grids and we start introducing more communication and other infrastructure into the system, we got to maintain that reliability.
Well, that's expectations. We have expectations of a good question from Lauren.
Yes, I'd actually like to challenge Walt a little bit and also hear from the rest of the panelists. The majority of global energy consumption comes from fossil fuels, and part of our role here at the summit is to transition away from that and find the potential mix of technology and solutions that doesn't lock us in. So you're against nuclear, but you had me going in support for a while with your presentation with the emphasis on reducing energy waste and changing mindsets. But then you were talking about natural gas and support for natural gas. So can you tell us why you think that should be part of the solution, and what are some other ideas from the other panelists as potential mixes of technologies to meet our energy goals?
If we could go cold turkey, as the English expression is, to kick our habit of addiction to fossil fuels absolutely overnight, with all the chills and shivers that would then follow, I think I would be in favor of taking this on simply for the health of the planet. But I don't think it's a feasible proposition for society. I think we're going to have to do this a bit more gradually. And therefore, if it's a question of picking the least worst of the fossil fuels, the least worst and the most supportive of the sort of transition I have in mind is natural gas, which for one reason or another, turns out also to be the one that is likely to be around a bit longer without being quite so detrimental as coal. I am not necessarily a great enthusiast for natural gas, and I'm definitely not an enthusiast for the new unconventional shale gas until we know an awful lot more about the consequences of fracking, of subterranean hydraulic cracking to release this gas. Some of the indications we've had so far are not very favorable about the possible contamination of underground water and so on. But if you think about the relationship between natural gas and what I call infrastructure electricity, they share a lot of common features. For one thing, you can generate locally and in very small efficient units using natural gas down to household level, with cogeneration and even trigeneration, producing heat and cold as well as electricity from the same fuel. So dramatically reducing the attributable carbon dioxide for each useful unit of energy that you get. So it is, some people sometimes call it a bridging technology. And I think that's likely to be I think if we go about this the right way, that is likely to be quite a significant feature of it. But I agree, it is still a fossil fuel, and in the long run, I hope we don't need to use it.
We have a question from up the back of the row, just there.
Good morning. Peter Krotke, Automated Solutions, Cambridge. Much of the discussion so far at the summit has been on discrete components of generation, transmission, and utilization. But as you mentioned, Walt, electricity is very much a process in technology. And as Bill mentioned, the customer expectation is to keep the lights on 99% of the time. Is there any work being done on transitioning or transforming from the grid system to a distributed and storage system? Because that's where I think a lot of the LDCs are struggling on how do you transition, keep the lights on, and go from the one to the other.
Well, a lot of work and a lot of actual progress is taking place. There is interesting developments. There is, for example, south of London in England, not London, Ontario, a town called Woking, which decided in 1990, when the British government liberalized its electricity arrangements, they decided that they would make themselves effectively independent of the rest of the electricity network. They had a town council and a visionary borough engineer. And they set about this in such a way that each successive stage of this gradual move toward independence financed the subsequent ones because it saved so much money for them. And if you Google the name Woking, W-O-K-I-N-G, you will find several million entries about Woking, simply because it was quite such a dramatic and successful example. The gentleman who did this was then recruited by the then visionary mayor of London to try and do the same thing for the megacity of London in England. Unfortunately, there was then an election and he was thrown out, and another much less visionary mayor was elected, and the first thing he did was to fire this engineer. So the city of Sydney recruited him. The city of Sydney has now got a program of the same kind to try and gradually decentralize, reduce the dependence on large remote central generation, bring up the profile of cogeneration and local district heating and local on-site generation of various kinds, and at the same time make the decision-making happen closer to the local level so that it is no longer remote, very, very high-level decision-making, but much closer to the people it's affecting. I think this process is happening in many parts of the world already. And of course, it's definitely happening in many parts of the developing world, where there are small local systems being installed in many rural areas.
Ted, you have a point.
There were days in Germany last summer where in the southern provinces, 20% of electricity need was met on those days using solar energy. So there are large-scale studies getting at exactly your question that are successful, that are working, and the grid can be rendered reliable using an admixture of renewables and legacy technologies.
So working didn't work in London, but will work in Sydney. That's great. Ma'am, you have a question.
Ding, a foreign member from China. Walt, sorry for putting you on the spot, but I really liked your idea about the change of mindset. I did a simple calculation that if North America reduced the per capita energy consumption to the level of the Germany, that will reduce the amount of energy saved will be enough, nearly like the total consumption of Latin American and African all together. So I was wondering if through sustainable consumption from the demand side, is there a way to maintain good quality life while without going the 30 terawatt? Because so far we have been discussing extensively how to meet the demand of 30 terawatts in future without really talking about can we really do it without going there. And also, when I was living in California, I just had a roommate who had tons of clothes and produced in China, cheap clothes, powered by dirty coal electricity, made by workers 12 hours working there. And is really necessary to have 100 t-shirts instead of, like I just borrowed this sweater and it just happened from Philippe, who told me a story and touched my heart. This is actually a sweater belonged to his grandfather and he's now wearing it. So if technology will be advocated by scientists and industries will advocate for technologies once it's coming to the commercialized phase, but who is there to advocate sustainable consumption? And if there is a way to meet our demand without going there 30 terawatts, who is there to inform the public that we do have a choice?
I think this is absolutely crucial. I've recently begun to realize that we have social systems in the world, and particularly the energy and especially the electricity system, which are based on what you might call the economics of flow, that keep track of stuff moving through the system, and it's the stuff moving through the system that everybody is concerned with, so that you have what used to be called planned obsolescence for consumer goods, motor vehicles, for example. They're built to fall apart, so that you actually have to replace them after a fairly short time. They don't have to be built to fall apart, but the companies are tooled up to keep selling new machines rather than to make very good machines much less often. It just happens to be the way our economies have evolved. And the alternative would be an economics of stock, in which you are actually trying to get the individual physical assets to be as high quality as possible, and of course maintainable and upgradable if that happens to be appropriate, but rather than just throwing them away and starting over for a new one. And this is one of the reasons why I like this idea of combining upgrading our user infrastructure for electricity and with infrastructure electricity, because those are both based on economics of stock, that you're trying to get the physical assets right, rather than worrying about electrons flowing through them. And the physical transactions, the business relationships and so on, all depend on a long-term concept of ownership and sales and maintenance and so on, rather than trading this afternoon at 3 o'clock 500 megawatt hours of electricity. It's quite a different concept.
Time for one last question.
Thank you. Mark MacArthur, forum member from Ottawa, Canada, and I'm putting this question to each of the panelists. If you knew that you had 1 year to live from today, where would you spend your time in transforming us to a new energy future? Would it be at the UN? Would it be with the government? Would it be talking to the private sector, public sector? Would you go back to the lab? How would you spend that time?
I would spend my time talking to people like you, to my, people of the generation of my children and grandchildren, because you're the ones that are going to have to make this happen. And if we can convey whatever insights we may have, to place them in your hands to make it, to give additional tools for you to cope better than we've been able to cope, then I think that's the best thing I could do.
There's a couch in my lab that is covered in spilled coffee and little bits of graduate student dandruff. I would spend all of my time on that couch, because that's where the breakthroughs are happening.
I'd actually try and spend my time trying to harangue politicians and decision makers, because it doesn't matter what research we do, it's not going to get out of the laboratory unless they regulate things to happen. And it doesn't matter how much we might want things to change, they're not going to change unless the decision makers make those changes. So, like for example, I really wanted to say that we don't have a choice sometimes in the way we use electricity, because our houses are not designed. I mean, we're forced. Our house is an oven in summertime. We would die if we didn't switch the air conditioner on. So if we design things better, then, and I think it needs to be done at government level, where we're forced to do these things, and it's not happening at the moment.
I think if I don't say I'd spend the time with my kids and my wife, I'd be in a lot of trouble when I get the mic off. Let me start with that answer now. After they've gone to sleep, I think the answer is you certainly on the policy side, on the informing the public, there's huge gains to be made there. But the reality is, as we've heard today and throughout the week, there's tremendous engineering runway left, if we want to borrow a phrase from earlier today, in all the areas. We need to get the politics right. We need to get the public policy right. It's not right today. We don't have the right price signals, as an example, to actually transition to a new system. So there's lots of work to be done. So well, I would try not to sleep. How's that?
Ladies and gentlemen, it's been a fabulous discussion. Please thank Bill Rosehart, Maria Skyllas-Kazacos, Ted Sargent, and Walt Patterson. Our summit participants will now adjourn to the summit room to actually do the hard work of bringing this to a reality. For those of you online, the next public lecture will take place later today. The speaker is David Keith, and the title of his talk is Technology, Energy and Nature, Human Values and Open Choices. Like all of the lectures we've had so far, it's highly recommended. Don't miss it. Don't forget to watch The Agenda with Steve Paikin tonight for another brilliant dissection of the energy issues. If you've missed some of the lectures, plenaries of the agenda, or the plenaries, the agenda, or you can catch up with them on tvo.org or wgsi.org. Thank you so much for taking part, and see you again tomorrow.